Hello, my name is Madison Lee, and I'm a master's thesis student in the electrical engineering department here at Mines. Today I'll be talking about my research I've been working on with my two advisors, Dr. El Shabani and Dr. Hadi. Today I will be talking about subgridding errors and standard and hybrid higher order finite difference time domain simulations. So the first thing I want to talk about is what is the finite difference time domain method. So finite difference time domain methods are commonly used to analyze electromagnetic wave phenomena. And what is it used for? Well, it's really important for analyzing problems involving wave propagation through urban infrastructures, wireless communications problems, RFID, and even antenna design, which is one of the most common uses. And then why do we need subgridding? Well, with Internet of Things and 5G, our frequencies are increasing rapidly, which creates these simulations that become very large electrically, which take up to days, weeks, depending on how large your problem is to solve. So subgridding, by splitting these problems into smaller sections, we can solve them quicker, but just as efficiently. So that's why this is going to be so needed as frequencies keep increasing. So one of the problems we want to focus on is the difficulties with 5G and Internet of Things device design. So when you're designing these devices that are at very high frequencies, there can be a lot larger of a problem to solve. Since it's meshing so small, it could take a very long time to solve. For example, if you had an 8x12 antenna array, it would require probably 300 gigabytes of memory that you would need, which would require many GPUs or very large and expensive computer to solve, and still would take a very long time. So our proposed solution is to use subgridding, which you can separate the problem space with fine meshes around articles of interest or the antennas, and then coarse grids elsewhere, or subgridding, where you could reduce that memory usage to under 30 gigabytes, which could be done on a single laptop. It allows these large domains to be solved accurately and efficiently with very little usage of resources and memory on your own computer. So the finite difference time domain subgridding process involves first updating the coarse magnetic fields in the x direction, which is what HXC stands for, magnetic fields in the x direction of the coarse grid, everywhere in the coarse grid. So that means all these blue arrows, we're going to be updating the entire grid. And then next, updating all the fine magnetic fields in the x direction everywhere in the fine grid using an updating equation. So all of these smaller blue arrows within this grid. Next, updating only the boundary magnetic fields and the coarse grid. So these large blue arrows we're going to update with the value we found from step 2 for the smaller blue arrow located underneath this. That exact same process, those 3 steps will happen again for the magnetic fields in the y direction. And then we'll move on to the electric fields in the z direction, which are these large green dots. We'll update those everywhere in the coarse grid, like we did the magnetic fields. And then we'll update the co-located fine grid fields, EZF, these tiny green dots with the value of the coarse grid on that same location. Now, since we don't have these fine grid electric field values between the coarse co-located ones, we will interpolate these across the boundary, which I will talk about in the next slide. After that, we'll update the non-boundary fine grid electric fields in the z direction, which are all of these darker green dots within the grid, the subgrid region. And now the same process, steps 1 through 10, will happen for every single time step within the finite difference simulation. So going into more detail, again, on the interpolation. So since we're only updating the fine grid electric fields along the boundary, using those coarse component values that we know already, at the corner and edge boundaries, we can interpolate between those 2 closest coarse nodes to find the value of the 2 fine nodes that are between it. For this example, we're using a 1:3 contrast ratio. So it will get 2/3 of the value of the node closest to it, and then 1/3 of the value of the closest farthest from it. So some results we have for 2D subgridding with a single subgrid region. This is the normalized difference equation we'll be using to calculate the error between a reference domain and our newly subgridded domain. So since as I explained earlier, we have a 1 to 3, a 1 to 9, 1 to 15, and a 1 to 27 contrast ratio, where the core cell size will stay constant at 3 millimeters, and the fine cell size will correspond to the given contrast ratio, smaller than the core cell size. So a domain we see over here is going to be 308 by 243 core cells with 10 layers of PML on each side. And then here we have a Gaussian source in the domain and a subgrid region surrounding that Gaussian source made up of 143 by 30 core cells. And for each contrast ratio, we can see this fine cell size decreases. So this grid right here is going to become denser and denser as we increase the contrast ratio, but it's going to remain a consistent core cell size. So now we can see all of the results here for the 1 to 3 cases, 1 to 9, 1 to 15, and 1 to 27, where we can see the S22 errors on the left side and the hybrid on the right side. And we can see on the S22 case, we have a second order calculation throughout the entire domain and a fourth order in the hybrid in the free space, but that same second order in the subgrid region. So the difference is that we can see here there is a large amount of errors propagating from the subgrid region further out in the S22 cases, where that's due to the error that's happening at the boundary as it passes from the inside of the subgrid outwards. And then we have on the right side the hybrid case where we're using a hybrid fourth order and second order calculation, where the fourth order is being calculated in the free space region and second order is remaining inside of the subgrid region. So that helps a lot of these boundary issues that we saw before, right at the edges where it's transitioning from subgrid to coarse grid. The fourth order calculation helps reduce a lot of those errors. As we can see here, it's a much slower in each case. Now when we actually look at those numbers, we're getting all the way up to a 78% improvement using the hybrid case specifically for the 1 to 27 contrast ratio. Then when we look at the CPU times, which is very important here, we're focusing on about a 96% amount of saved time compared to the reference domain with no subgridding, where you can even see here the 1 to 27 took about, this is in minutes, so that is 3 days, and then the subgridding domains took only about 8 hours. Then when we look at the memory breakdown, we can see the amount of memory saved gets all the way up to 88%, which is very significant for the 1 to 27 contrast ratio, where the subgridding domains take about 2 gigabytes consistently and all the way up to 21 for that reference. So when we look at 2D subgridding for multiple subgrid regions, which could be useful if you have multiple areas that you're trying to grid with different contrast ratios. They might be smaller slots in an antenna design. So you could use multiple grids to cover each one of those separately. So here we have the hybrid finite difference time domain problem space on the left here with the results on the right. If we go over the domain, it's a little bit larger than the previous one just to accommodate the extra subgrids. So you can see here we have 3 subgrids. There's 2 with a contrast ratio of 3 and 1 in the middle with a contrast ratio of 9. And then again, another Gaussian source, but now instead of being inside the subgrid, it is outside the subgrid. So that's why we're seeing some of these errors here right at where the source begins. But really, we can just use this to look at the propagation outwards, where we can see on the right here the error using the same calculation as before. We have pretty low errors, about 1 to 2%, which is pretty acceptable for 3 different subgrids with different varying contrast ratios. So a lot of the achievements that we've talked about today, we're seeing very acceptable levels of error in both the S22 and hybrid domains up to contrast ratios of 27, as well as a significant speed up in CPU times and reduction in memory usage, which is very ideal for subgridding situations, and also a successful implementation of multiple subgrid regions in a 2D domain. So going forward, we'll be integrating subgridding into a 3D computational domain so that we can begin testing on realistic scenarios such as filter and antenna array problems. And hopefully going up to higher subgrid ratios of 30, 90, past 100. Sometimes those are necessary with the very high frequencies we have. For 5G, going all the way up to 60 gigahertz is a very small meshing ratio you will need. So recent publications we've had, I published 2 conference papers, one last year and then one this year on the work I talked about today. And we've also recently submitted a journal paper covering a lot of what I've gone over in those conference papers and then a little bit more. So a few achievements we have with those. Last year, whenever I presented at the student paper competition for the ACES conference in Miami, I actually placed 3rd in the competition, which was really exciting since I was still an undergrad then, and actually the only undergrad in that competition, so that was super exciting. So one of the main takeaways I want to talk about is that this research could pretty much revolutionize the antenna design process, with simulations taking fraction of the time that they would have to at such high frequencies that we're getting to now with 5G and Internet of Things, and probably going even higher. We don't know, it gets higher every day. So this is the kind of software that we will need to get the work done for the demand that exists. But yeah, thank you so much for listening to this presentation. If you have any questions, feel free to email my email listed here or visit our website here, which will give you information on what everyone in the group is working on, which is pretty cool. Thank you.